This time, I'm going to talk about distance metrics in machine learning and their implementations in Python. Distance metrics play an important role in machine learning. They provide a strong foundation for several machine learning algorithms like k-nearest neighbors for supervised learning and k-means clustering for unsupervised learning. Different distance metrics are chosen depending upon the type of the data. So it is important to know the various distance metrics and the intuition behind it. In this video, I'm going to introduce several popular distance metrics as following. Let's go through them one by one. First, let's talk about Euclidean distance. Euclidean distance represents the shortest distance between 2 points. Now, let's think about this example. There are two objects located in this two-dimensional space. Object 1 is located at x1, y1, and object 2 is located at x2, y2. So, the distance between object 1 and object 2 can be calculated with this formula. This is the Euclidean distance. Another distance metric is called Manhattan distance. It is called the Manhattan distance because it is the distance a car would drive in a city, for example, Manhattan. Personally, I work at Manhattan, so if I want to go from point A to point B, I can't draw a straight line and go through because there are buildings in these blocks. So I have to go either this way or I go this way. You can see, although I can take different routes, but the distance will remain the same. So if you want to calculate Manhattan distance, you will use this formula. You take the difference between x coordinates and take the difference between the y coordinates and you sum those up. Like in this example, the x coordinates difference is this one, and then y coordinates difference is this one. You just sum those up. Even though you can take different route, like this blue line, but if you think about the result, for the x coordinate, this distance is equal to this distance, and this distance is equal to this distance, and also this distance is equal to this distance, and the same logic with y coordinate. And so if you sum those up, it will give you the same result. Then there is a distance metric called Minkowski distance. Minkowski distance is a generalized form of Euclidean and Manhattan distance. It is a generalization of Euclidean and Manhattan distance measures and adds a parameter called the order, or p. You can see Minkowski distance is calculated with this formula. So the p is the order parameter, when P is set to 1, it is equal to Manhattan distance. So basically it will be the same with this distance. But when P equal to 2, it will be Euclidean distance. It will be this distance. And also P can take 3, 4, 5, or 6. Later, I'll show you all the results when we set different value for P for this Minkowski distance. Then we have this cosine distance and a concept called cosine similarity. So the relationship between cosine distance and the cosine similarity is cosine similarity equal to 1 minus cosine distance. The cosine similarity is a measure of a similarity between two non-zero vectors. It is calculated at the inner product of the two vectors that measures the cosine of the angle between them. Basically, cosine distance doesn't care about the length of the vector. It only considers the direction of the vector. When we calculate cosine similarity, we use this formula. You can see if the theta is 0, cosine theta will be 1 and cosine similarity will be 1. That means they are the same. But if vector A and vector B are pointing to different directions, then cosine theta will be minus 1 and cosine similarity will be minus 1. Now let's talk about Mahalons distance. Instead of considering distance between 2 points, Mahalons distance is one type of the statistical distance measure which is used to compute the distance from the point to the center of a distribution. So, for example, we have a distribution like this, and then we have the center of this distribution. If we have a point here, Mahalons distance will mean it calculates the distance between this point and the center of the distribution. So, Mahalons distance is ideal to solve the outlier detection problem. The distance of a point P from probability distribution D is how far away standard deviation P is from the mean of the probability distribution D. Later, I'll show you how to detect outlier with this Mahalons distance in Python. When we calculate Mahalons distance, we use this formula. D squared is the square of the Mahalons distance, and x is the vector of the observation, this x, and m is the vector of mean values of independent variables. So this is the mean value. C with power minus 1 is the inverse covariance matrix of independent variables, and t is transpose of this x minus m vector. Later, I will show you how to calculate Mahalons distance with Python. Another type of statistical measure is Draghard distance. It takes into consideration the intersection or overlap of attributes between two objects between which the distance needs to be found. For example, we have this A collection and also this B collection. They have overlap here, and Draghard distance is calculated by taking this overlap portion divided the union of A and B. So you consider all A and all B as denominator. Next distance metric is called Chebyshev distance or chessboard distance. It is best defined as a distance metric where the distance between two vectors is the greatest of their differences along any coordinate dimension. Think about this two-dimensional space. Then the Chebyshev distance can be calculated with this formula. Think about this chessboard. The distance between this queen and those positions is 1, and next round will be 2. You may understand Chebyshev distance this way. Imagine you are in a library and your friend is standing here. There are a lot of bookshelves blocking your view because they are very tall. If you are standing here, you can either go this way, 1 block, 2 block, or you go this way, 1 block, 2 block, in order to find your friend. So Chebyshev distance is similar with this one. This is just like on the chessboard. If you want to do a checkmate, you can either do this way or do that way. Canberra distance is a weighted version of Manhattan distance, which has been used as a metric for comparing ranked lists and for intrusion detection in computer security. If you have two vectors, P and Q, and you can calculate Canberra distance with this formula. Lastly, we have this Hamming distance. Hamming distance measures the similarity between two strings of the same length. The Hamming distance between two strings of the same length is the number of positions at which the corresponding characters are different. Think about those two strings. One is A, one is B. So we will compare all the digits one by one. So there's 1 difference, 2 difference, and 3 differences between those two strings. So in this example, the Hamming distance is 3. And also you can draw a graph like this, because between those two digits, there is one difference. So the distance is 1. But between those two digits, you have two differences. So the Hamming distance between 0, 0 and 1, 1 is 2. Okay, now let's go to Python to see how can we calculate all those distance metrics. I put all the calculation for those distance metric in the same file except for Mahalons calculation. I will upload both files to my GitHub so you can download and try it by yourself. In order to understand the calculation, I didn't use any built-in function or any Python package for the calculation. I just wrote the code with the calculation manually. Okay, now let's run the program. You can see I use the same data point for all those calculations. For Euclidean distance between those 2 points, this is 4-dimension data points. It's a 3.742. And for the Manhattan distance, you can imagine it will be larger. It is 6. And then I calculate the Minkowski distance with different parameter p. If p equal to 1, as I mentioned before, it will be equal to Manhattan distance, which is 6. And if p equal to 2, and it will be 3.742, which is equal to Euclidean distance. When p equal to 3, 4, 5, or 6, you can see the distance will become shorter and shorter. This is quite interesting because in our world, the Euclidean distance is the shortest distance. But with this Minkowski distance, when you have higher p, it will give you even shorter distance. So maybe this is higher dimension distance, and we can't imagine those like by our instinct. As I mentioned before, cosine similarity only care about the direction of the vectors. It doesn't care about the magnitude of the vectors. In this example, the cosine similarity between our 4-dimension vector is 0.696. And then I calculated the Draghard similarity and Draghard distance. As I mentioned before, Draghard distance equal to 1 minus Draghard similarity. So let's take a look at this example. In this example, we have 0 in common, 2 in common, and 5 in common. So we have overlap of 3. And in total, how many numbers do we have? We have this 0, 1, 2, 5, 6. Here we have 3, 4, and also 7. So in total, and also 9. In total, we have 9 numbers. So we have 3 in common out of total 9 numbers. It's 3 divided by 9. So this is 1/3 or 0.333. And the distance will become 1 minus 0.333, which is 0.667 or 2/3. Then I calculate this Chebyshev distance between those two vectors, which is 3, and the Cabra distance is 1.3, and this Hamming distance between those two strings is 2. We can take a look. You can see GA is the same, but the third character is different. And then TA is the same, but you see this C replaced by T, so it's different. And the last one is the same. So there are two characters are different between those two strings. That's why the Hamming distance is 2. Now let's take a look at this Mahalons distance. In order to calculate Mahalons distance, I use this data file, airquality.csv. I will upload this file to my GitHub as well, so you can download it and use it. I have index for those data points, and then I have ozone, solar, wind, temp, month, day. But for this example, I only use ozone and temp. I will do some cleanup first, and then I will calculate covariance, and then I will calculate the distance. In order to detect outlier, I've used cutoff as 95%. So the threshold is 95%. And then, after I decided the center of the distribution, I will draw an ellipse and then draw all the data points in order to see all those outliers. Let's run the program. You can see I calculated all those distances, and then I can see there are 4 outliers. And from this graph, you can see my distribution is like this, and this is the center of the distribution, and all those 4 data points are outliers. This is my brief introduction about distance metrics in machine learning and how you can implement them in Python. Please provide your comments and subscribe to my YouTube channel. Thank you very much for watching.